Hello, this is Mario from ODEON. In this video, we will talk about the calculation parameters in the room setup and how to adjust them to get reliable results. You can go to the room setup by clicking here. The first parameters you will see are the impulse response length and the number of late rays. These are the two most important parameters that you should always check before running your first calculation. In our tutorial video about point responses, we used preliminary values suggested by the software. However, after you make a calculation, you can take a look at some of the results to gauge the reliability of the calculation. Then, you can readjust the calculation parameters and make a new calculation with results that are more reliable. The impulse response length is how many milliseconds of the decay curve will be calculated. If the impulse response length is too short, the decay curve will be cut off too early, and there might not be enough of a decay range for a reverberation time regression. In that case, it will not be possible to derive some reverberation times, particularly T30, since it requires a larger decay range than T20. Parameters that were unable to be derived will be shown as asterisks in the results. But if the impulse response length is disproportionately large, you might be including unreliable results at extremely low energy values into the regression. Plus, this will extend the calculation time. A typical guideline for defining the impulse response length is to make it at least 2/3 of the expected reverberation time, which gives enough of a decay range to calculate T30. You can find an expected reverberation time with this quick estimate. ODEON will automatically update the impulse response length with a suggested value, which will be around the maximum reverberation time found in the quick estimate. When defining the value manually, the easier and safer way would be to simply enter the maximum reverberation time found in the quick estimate. Also, notice that the quick estimate calculates the room's Schroeder frequency. In our tutorial video on importing geometries, we explained how you could use the Schroeder frequency as a rough estimation of what is the lowest frequency that is diffuse enough to be calculated reliably in ODEON. Remember that in practice, results at frequencies slightly lower than the Schroeder frequency can still be reliable. Also remember that the quick estimate can be accessed from the material list as well. Keep in mind that the reverberation times in the quick estimate are not final results. They are mainly useful for defining an impulse response length as we showed, and for quickly getting some rough results when changing through many materials. Accurate reverberation times are obtained from the calculations performed in the job list, such as multi-point responses and single-point responses. Since the appropriate impulse response length is dependent on the reverberation time, it is consequently dependent on the materials in your room. Therefore, remember to update your impulse response length each time you change materials in your room. If you plan to go back and forth between different material setups, you can just set a fixed impulse response length that is long enough to accommodate to the most reverberant of your setups. For the number of late rays, we will briefly explain ODEON's calculation methods. Reflections will be classified as early reflections or late reflections depending on the reflection order. The transition order is the reflection order at which ODEON makes the distinction between the two types. The default transition order is 2, meaning that reflections up to the second order will be considered early, and higher reflection orders are considered late. This can be changed, but it is an advanced parameter that will be addressed in our video on specialist settings. For the early reflections, ODEON will use ray tracing to find valid image sources, as well as generate secondary sources for early scattering. For the late reflections, ODEON uses the ray radiosity method. These are explained in more detail in our video on ray tracing and hybrid methods in ODEON. Then, this number of late rays is the number of rays used for the late reflection stage. If this is too low, it can harm the calculation accuracy. But if it is too high, again, it will extend the calculation time. Initially, ODEON will suggest a number based on your geometry. Here, you will see 3 buttons. These automatically suggest numbers of late rays, plus other parameters in the specialist settings that we will not address in this video. Survey is for quick simulations, although the accuracy might not be enough for final results. Upon clicking the button, the number of late rays is updated, but the field becomes yellow as a warning that this number is low for accurate results. The engineering setting is a modest starting point. In some cases, this may already be good enough for reliable results, but we would still encourage you to double-check the reliability of your results and increase the number of late rays if necessary. The precision setting will suggest a very high number of rays. While this is excessive for most cases, there are certain cases which do require a high number of rays for reliable results. For example, coupled rooms with very different reverberation times, or if you are simulating transmission, since only 10% of rays pass through transmission walls. Additionally, the precision setting can be recommended for academic research applications. There are a couple of ways to find out if you might need to repeat the calculation with more rays. One of them is the reflection density parameter. Generally, we would recommend the reflection density to be above 30 per millisecond. Another way is to check the amount of nonlinearity in the decay curves, which is indicated by the decay parameters and the curvature parameter. In a highly diffuse room, the decay curve will ideally be a straight line. However, if the number of late rays is too low, this can result in some bumps or sharp drops in the decay curve. So, a high value of nonlinearity would indicate that you may need to repeat your calculations with a higher number of late rays. The decay parameters measure the nonlinearity of the curve across two different ranges. T20 is the nonlinearity from the beginning of the decay to a drop of 20 decibels, while T30 is the nonlinearity from the beginning of the decay to a drop of 30 decibels. Ideally, the decay parameters should be below 10. If you have values higher than 10 in several octave bands, you may need to increase your number of late rays and repeat the calculation. The curvature parameter relies on a different principle. With a straight decay curve, T20 and T30 should give practically the same values. However, a bent decay curve will produce different values between T20 and T30. So, this curvature parameter is a measure of the curvature of the decay curve, and it is calculated through a ratio of T20 versus T30. If the curvature value is higher than 10, you will need a number of late rays even higher than suggested by the precision setting. So, the decay and curvature parameters can indicate a low number of late rays for rooms where you expect a linear decay. However, there are some cases where the sound field of the room is not diffuse, and therefore the decay curve will inherently be bent, not because of a lack of rays, but because that is the behavior of the room itself. For example, an uneven distribution of absorption can result in a two-dimensional sound field in the room, meaning the sound is reflecting back and forth mainly across two axes rather than all three. This produces a bent decay curve. In these cases, you will still need to increase your number of late rays according to the suggestions. But it will not necessarily decrease the decay and curvature parameters. Remember to also rely on the reflection density parameter, which is useful across all types of rooms. A good way to examine decay, curvature, and reflection density is by calculating a multipoint response with receivers scattered across the whole room, and then looking at the statistics. The Statistics tab does not show broadband parameters such as reflection density. Instead, you can find statistics both for frequency parameters and broadband parameters in the Energy Parameters tab. You can jump to the statistics tables for frequency and broadband parameters with these buttons. If you have ODEON, auditorium, or combined, you can visually inspect the decay curve for individual receiver positions with your current number of late rays in the Decay Curve tab of the single point response. Again, if you see sharp drops in the decay curve, this means you may need more late rays. To explain this ray loss allowed parameter, I will explain what is ray loss. In ODEON, lost rays are rays that have escaped from the model due to imperfections in the geometry. This is something that should be avoided as much as possible, since the rays need to keep reflecting in the room in order to produce the decay curve. Therefore, ODEON will interrupt calculations and issue a warning if there is a considerable amount of lost rays. However, geometries are rarely 100% watertight, so a small amount of ray loss can be acceptable. Then, this ray loss allowed parameter is the maximum tolerance of lost rays before ODEON interrupts calculations. Although ODEON is primarily a room acoustic software, it can also calculate outdoor acoustics. Just keep in mind that ODEON does not calculate the bending of sound due to atmospheric conditions. So, we would recommend to keep outdoor models within a few hundred meters in size where this effect is not so prominent. While performing outdoor calculations, one can expect that practically all rays will be lost. So, the ray loss allowed should be set to 100% for outdoor modeling. And for outdoor models, a much lower reflection density is acceptable, down to 10 per millisecond or even lower. Down here, we have the specialist settings. These are advanced settings that are not too important to adjust. In fact, it is typically better to leave them untouched. We will explain them in our tutorial on specialist settings. Now we will go to the Air Conditions STI Parameters Model Check tab. These background noise values are only relevant for calculating STI, and they don't affect any other calculations. So, they will be addressed in our tutorial for calculating STI. These air-conditioned settings are for calculation of air absorption, which is particularly important for highly reverberant rooms such as large rooms. This is because, since the sound is propagating through the air for a long time, then the absorption of air has a bigger impact. You can enter the temperature in degrees Celsius, and it will also show the conversion in Fahrenheit next to the input box. And down here, you can enter the relative humidity. Alternatively, you can turn off air absorption, though we don't recommend it. Finally, these model check parameters are the maximum acceptable warp and wall overlap when running the 3D Geometry Debugger. Remember that you can access the 3D Geometry Debugger here. That concludes this tutorial, and we hope you have found it useful. Good luck!